If the constituent particles, such as atoms, ions, or molecules, in a solid crystal are arranged in a regular fashion, then the crystal is said to be an ideal or perfect crystal. However, no crystal in the universe is perfect. Almost all the crystals encountered in practice suffer from defects. This happens when the crystallization process occurs at a fast or moderate rate. In order to avoid these defects, the process of crystallization is conducted at an extremely slow rate. However, even the crystals so obtained are also not free from defects. These defects in solids are broadly classified into point defects and line defects. Point defects are the irregularities or deviations from the ideal arrangement around a point or an atom in a crystalline substance. These may arise in a crystal due to one of several reasons: the absence of a constituent particle, the presence of a foreign particle at the lattice site, the presence of a foreign particle at the interstitial site, the displacement of a particle to the interstitial site. Point defects are classified into three types, namely stoichiometric defects, non-stoichiometric defects, and impurity defects. Let's first learn about stoichiometric defects. A stoichiometric defect is a defect by which there is no disturbance in the stoichiometry of the solid. These are also called intrinsic or thermodynamic defects. Stoichiometric defects are further classified into vacancy defects and interstitial defects. The defect in which a constituent particle is missing from the crystal lattice is known as a vacancy defect. This defect develops when a substance is heated. You can clearly observe from this figure that some of the constituent particles are missing from the crystal lattice. As a result, some vacancies are created. The major consequence of a vacancy defect is that the density of the substance decreases. On the other hand, an interstitial defect arises when some of the constituent particles occupy the interstitial sites in a crystal lattice. From the figure, it is evident that some constituent particles occupy the interstitial sites in a crystal lattice. As a result of this defect, the density of the substance increases. This holds good only for non-ionic solids. Ionic solids must always maintain electrical neutrality. Rather than a simple vacancy or interstitial defects, ionic solids show Frenkel and Schottky defects. Now let us learn about Frenkel defects and Schottky defects. A Frenkel defect is caused if some of the ions of a lattice occupy the interstitial sites by leaving a corresponding number of normal lattice sites vacant. You can see this from the figure here. This creates a vacancy defect at the original site and an interstitial defect at its new location. A Frenkel defect is also known as a dislocation defect. It does not influence the density of the substance. This type of defect occurs in compounds with ions of different sizes. Since cations are smaller than anions, cations can easily fit into the vacant spaces in the lattice. For example, In a silver chloride crystal, an Ag+ ion occupies an interstitial site by leaving a vacancy at the original site. Zinc sulfide, silver bromide, and silver iodide are other examples that have Frenkel defects. A Schottky defect is caused if some of the latter sites remain unoccupied. The number of missing positive ions is equal to the number of missing negative ions, and thus the crystal remains electrically neutral. Unlike a Frenkel defect, a Schottky defect causes a decrease in the density of a substance. This defect is commonly observed in compounds in which the cations and the anions are of almost the same size. Sodium chloride, potassium chloride, and cesium chloride are well-known examples of this defect. The number of Schottky defect in ionic solids is quite significant. For example, in a crystal of sodium chloride, 1 million Schottky pairs per cubic centimeter are noticed. You are already aware that point defects are of three types, namely stoichiometric defects, impurity defects, and non-stoichiometric defects. In the previous module, you studied stoichiometric defects. You will learn about the other two defects in this module. Let's start with impurity defects. You already know that it is almost impossible to obtain a perfectly pure substance. Purification is a costly process. In general, analytical, reagent-grade chemicals are of high purity. Yet, few of them are more than 99.9% pure. This means that a foreign atom, ion, or molecule is present in the crystal. In such a case, we can say that the crystal has an impurity defect. For example, during the crystallization of molten sodium chloride, if it contains a small quantity of strontium chloride, then some of the sites of sodium plus ions are occupied by strontium plus 2 ions. Each strontium plus 2 ion replaces 2 sodium plus ions. Strontium plus 2 occupies the site of one sodium ion, and the other site remains vacant, which results in the creation of cationic vacancies in the crystal. The number of cationic vacancies is the same as the number of strontium plus 2 ions present in the crystal. Another similar example is the solid solution of cadmium chloride and silver chloride. The defects that we discussed so far do not disturb the stoichiometry of crystalline substances. However, non-stoichiometric defects affect the stoichiometry of crystalline substances. Let's first define a non-stoichiometric defect. The defect that causes the ratio of the number of cations to anions to be different from that indicated by the ideal chemical formula is known as a non-stoichiometric defect. Non-stoichiometric defects are of two types, metal excess defects and metal deficiency defects. Let's first discuss metal excess defects. A metal excess defect may arise in crystals due to anionic vacancies or the presence of extra cations at the interstitial sites. Metal excess defects that occur due to anionic vacancies can be illustrated by taking sodium chloride as an example. When crystals of sodium chloride are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the sodium chloride crystal. The Cl- ions present in the sodium chloride crystals diffuse to the surface of the crystal and combine with the sodium atoms present there to give sodium chloride. This happens because sodium atoms lose electrons to form sodium ions. The electrons so released diffuse into the crystal and occupy the anionic sites created by the diffusion of the chloride ions. As a result, the crystal now has an excess of sodium ions. The anionic sites occupied by unpaired electrons are called F centers. Here, F stands for Farbenzenter, a German word that means color center. The anionic sites occupied by unpaired electrons are called so because they impart color to the crystal. For example, excess of sodium makes sodium chloride yellow. Excess of lithium makes lithium chloride pink. And an excess of potassium makes potassium chloride violet. The reason for this phenomenon is the excitation of the electrons present at the anionic sites of the crystal when they absorb energy from the visible light falling on it. Now let's see how a metal excess defect arises due to the presence of extra cations at the interstitial sites with zinc oxide as an example. Zinc oxide is a white solid at room temperature. On heating, it loses oxygen and turns yellow. Now there is an excess of zinc in the crystal and its formula changes from ZnO to Zn1 plus XO. The excess zinc 2 plus ions move to the interstitial sites and the electrons to the neighboring interstitial sites. The other class of non-stoichiometric defect is metal deficiency defect. This defect may arise due to cationic vacancies. It occurs when positive ions are missing from its crystal lattice. A typical example of this type is FeO, which is mostly found with a composition of Fe 0.95O. It may actually range from Fe 0.93O to Fe 0.96O. In crystals of FeO, some Fe2 plus cations are missing, and electrical neutrality is maintained by the presence of the required number of Fe3 plus ions. Iron sulfide, nickel oxide, and titanium oxide are other examples that have this defect. Line defects are the irregularities or deviations from the ideal arrangement in entire rows of lattice points. These arise mostly due to the misalignment of particles or the presence of vacancies along a line.